Na ja, wir können auch noch eine Minute warten. Okay, can I continue, or is somebody still outside? Okay, let's just continue. I wrote 3 references for the whole ideas about the single-valued polylogarithms and the single-valued zeta values on the blackboard. The first paper I want to recommend is a paper from Francis Brown from 2004. It's called Single-Valued Multiple Polylogarithms. I'm sorry for the shortcuts in one variable. And if you want a version where it is easier, or at least it was for me, to get used to the formalism, you can look at a paper from Lance Dixon, Claude Doerr, and Jeffrey Pennington, 1207-0186, where you have a applied physicist excerpt together with a couple of examples of Brown's formalism. So I learned it more from that paper than from Brown's original one. Nevertheless, Brown's original one is also a very nice one. And then you could, and that is something I will not be able to cover, immediately ask, what about if you have polylogarithms which are not just in one variable, but polylogarithms in multiple variables? Then you will have to consider multiple complex planes, and in each of these complex planes, all the branch cuts will have to cancel. And indeed, this does exist as well, and there's a paper which is from Claude Doerr and I think 6 different authors from summer 2016, where they resolve or calculate amplitudes in Enikov-4 super-Yang-Mills theory and multi-Raggi kinematics. And in one chapter in there is an explanation how to deal with single-valued polylogarithms in multiple variables, and there is no limitation. You can have an infinite number of variables. It's just combinatorically very involved then. So if you want the multivariable version of what I sketched on the board, that's the paper to get started with. Now, let's go to the back to the zeta values. I want to define zeta single-valued as, or not only me, but everybody does it, as the single-valued of the appropriate index evaluated at 1. And if you define these values, you can do the math and get a couple of properties for these zeta values. The first and most important one is that zeta single-valued of 2 is 0. So the even zeta values, and if 2 disappears, also all the others will disappear, because the algebraic structures for the subclass of single-valued zeta values is inherited from the usual zeta values. All the even single-valued zeta values will disappear. What is furthermore very nice is that this is nothing else as the value at 0 from the Bloch-Wigner d-logarithm, which appeared in Eric's lecture at the very end. Because the Bloch-Wigner d-logarithm is the single-valued version at weight 2 of the logarithm. So this d is the mathematical notion usually for the Bloch-Wigner dialog. Now, furthermore, you can write down theta single-valued of an odd single argument, and this is nothing else as twice zeta without single-valued of the same argument. So zeta single-valued 3 is twice zeta 3, and that's valid for all n larger and equal to 1. And you can play more interesting games and write down what zeta single-valued 5,3 is. That's just 14 zeta of 3, zeta of 5, and more complicated things to follow. While these things can easily be derived from sorting out the appropriate corresponding logarithms, already here you would have a g of length 8, because we have weight 8 here, so you get 8 ones or zeros in the logarithm, and resolving the single-valued condition at length 8, or weight, at length 8 in the letters is not very difficult, but once you get to 14 or 18 or 22, what people have done, then you're running into trouble because of computational time you need. Combinatorics is going to kill you. Mathematically, it is one thing I would like to mention here. These single-valued zeta values are precisely the values of iterated integrals on the Riemann sphere with 3 marked points, which are obtained by integrating from 0 to 1, but now independent of the way we actually choose the integration contour. During the first lecture, I have mentioned that we're looking at the Riemann sphere point at infinity, and that I would like to imagine the integration contour for the usual zeta values for the iterated integral always between 0 and 1, because that's a nice way I can fix it to be like that, and I can express all the zeta values integrating on the real line between 0 and 1. Now, if I would take this contour and move it away from the 0, 1 real line, I would actually get into trouble, because then I would have to think about branch cut structure. The branch cut for one logarithm would be in the negative real axis, and I would get into all kinds of trouble. Now, single-valuedness removes this type of thing, because we have been ensuring that there is no branch cuts I have to take care for, and I could easily calculate a single-valued zeta value by choosing whatever kind of contour I would like to have on the Riemann sphere. So this is a statement which is in the original paper by Francis Brown, and I think it is a very nice statement. While for the usual zeta values, you have to really be careful what you mean by integrating on the Riemann sphere, and you need to specify, I did this particular path, you can choose others. The single-valued zeta values, they are completely homotopy invariant on the whole sphere. That is, I can choose any integration contour from 0 to 1, and I'll get the same result. Now, in order to finish today's lecture, I want to connect the single-valued concept with the F alphabet. So the F alphabet I had introduced for defining a better basis for multiple zeta values. And now let us have a look how these single-valued zeta values do actually look in the F alphabet. That's the official shortcut, single-valued MZVs. Consider single-valued multiple zeta values in the F alphabet language. It turns out that the single-valued version of a zeta value, Fi1 to Fir, single-valued, can be obtained as the sum from I equal 0 to R, so that should have R words here. Letters, my apologies. And then you basically take the initial word and cut it at position 0, 1, 2, 3, and so on. That's the running index here. Let me call it J. And then take the word and take the letters F1 to Fj, and then take Fr to Fj plus 1. So that is, you cut your word into two pieces, you leave the first piece standing here, and you reverse the ordering of the other piece. I have unfortunately removed the single-valued versions for the polylogarithms, but there the rule, you might have guessed, was exactly that one. You would take the indices, so the 0, 1 word, cut it at every possible position, take the first one and plug it in the polylog with respect to z, reverse the second part and plug it into the polylog with respect to z bar. The advantage of the F alphabet is now that the formula I wrote down here is valid even if you're getting to something which corresponds to an iterated integral of length 4. So there will be no other additional zeta terms which will leave the pattern, but the F alphabet resolves that kind of problem for you. And in the F alphabet, it is very natural and very simple to write down what a single-valued zeta value actually is. So in a sense, the two small blocks, 15 minutes and 15 minutes again, single-valued zeta values, and this other representation in terms of the F alphabet, they come together here. The single-valued projection, as it is called, is neatly connected in that formula. Yes?
I'm just wondering, is there maybe a shuffle product? Or if there is none, can you explain why this is an algebra?
Is here. Sure, yes, yeah, exactly.
Usually with kind of recursive formulas, I have a
Yeah.
calculation using the encoded solution why this is compatible with products. So for that, I would have expected a shuffle.
I'm not sure actually as well. I wrote the formula down from my head and I didn't think about it, so I might perfectly be wrong here. I will just check. Are you sure? You are not sure either? I'm sorry, I'm not sure either as well. Might well be that there's a shuffle product here, but as far as I can remember, there was none. But no, let's just, I'll tell tomorrow. Or do you know?
There might also be some indexing issues. I mean, you probably want ISO R and stuff. But also, I think there's only two terms for R equals 2. Right? Don't you want the answer for R equals 2 to be just the one order and then the reverse order with equal weight?
So you're saying it's from 1 to r minus 1?
Or maybe 1 to r?
Ah, my apologies. So I should have double checked the formula. So the structure should be like that I'm very sure about. So if you have the indices fi1 to ir, yes, then I want I1 to ij. Thanks for pointing that out. FIR and FIJ plus 1. But the other one is more serious.
I think this sounds right. Because if you just take a single f, right, you want it to become 2f for the single data.
Yeah, so I want to do it on the left-hand side and on the other-hand side. And I also checked right now when you asked the question that for the polylog, you will also get the original polylog. If you take the single-valued polylog of 0, 1, 0, 1, say, you would get G 0, 1, 0, 1 of Z, and the full word also reversed, which would be an argument for the limits to be from 0 to R. Yeah. So I will check, and I assume other people will check as well whether there is here a shuffled product. So leave a little of space if you write it down. Now, in view of time, I wanted to tell a little about the PSLQ formalism, but we can also do that tomorrow. I'm right at the 90-minute threshold, and considering that it's already rather late, I will not put another 10 minutes. I will just get started with that tomorrow then. Okay, thanks for the